In the previous lecture, we spoke about the parallel axis theorem, and we said that we can use this theorem to help us calculate what the moment of inertia of a rotating object is. Now, in this lecture, we're actually going to prove the parallel axis theorem. So we begin with the following claim. So our parallel axis theorem, which gives us the following formula. The moment of inertia of the object is equal to the sum of these two quantities, where ICM is simply the moment of inertia of the object when it rotates about an axis that goes through the center of mass. And md squared is m is simply the mass, and d is simply the distance between the axis that goes through the center of mass and the axis about which our object actually rotates. So note that those two axes are parallel to one another. So we want to show that this is in fact true. So let's begin with our proof by taking some randomly shaped object. So let's suppose we have a three-dimensional object that has some shape, and we take the cross-sectional, the two-dimensional cross-sectional area of the object and draw the xy plane such that the center of the mass of that object lies directly at the origin. So this is the origin, our xy axis. The origin is at this point, and that's exactly where our center of mass of our two-dimensional object is. Now the object actually rotates about some point that is not the center of mass. So let's choose that point to lie here. So the point W, given by the coordinates xw, yw, is the point about which our object is actually rotating. Now notice that the z-axis, which is coming out of the board and going into the board, goes directly through the origin. So it goes directly through the center of mass. And this z-axis is parallel to the axis about which our object is rotating, the axis that goes through our point W. Now, suppose xi, yi, and mi represent the coordinates and the mass of the ith particle. So we take our mass that has the following shape and we break our object down into square particles as shown. And the ith particle, where ith is simply the number of that particle, has the mass mi and has the position xi, comma, yi. Now the distance between W and this particle and the square particle is given by our formula, our distance formula. So this distance squared, the square of the distance from the ith particle to the point W, is given by this equation. Xi minus xw squared plus yi minus yw squared. So this is the distance from W to this particle squared. Now notice this distance d is simply the distance between our z-axis, our axis that goes through the center of mass, and the axis W about which our object is actually rotating. So let's begin by calculating what I is. Our end goal is to show that I is equal to exactly this formula. So let's begin. I is equal to the moment of inertia of the object that is rotating about the axis that goes through the point W is equal to, well, we have to sum up the product of the mass and the distance squared, where the mass is simply the mass of each particle, like the particle shown here, and the distance between the point about which our object is rotating and that particle. So this is exactly what we get, where mi is the mass and this distance is the distance between them squared. So let's actually take this and expand it. So we have xi minus xw multiplied by itself and yi minus yw multiplied by itself. And let's actually multiply all these guys out. Xi times xi gives us xi squared, xi multiplied by negative xw plus negative xw multiplied by xi, so negative 2xw xi, and then negative xw multiplied by negative xw, positive xw. And the same exact thing is done for this quantity. So we get the following result. So now let's distribute this summation mi, and let's rearrange our quantities just a bit. So we combine x squared w and y squared w, and we combine xi squared and yi squared. We get the following 1, 2, 3, 4 quantities. Now note, because we choose the origin to be the center of mass, and xcm is equal to 0 and ycm is equal to 0, these entire quantities, the sum of mi xi and the sum of mi yi, will be 0. So these entire terms goes to 0, and we're simply left with these two summations. Now, note the summation, this summation, our sum of the products mi multiplied by xw squared plus yw squared is simply our md squared. So this quantity is the same thing as md squared, where this mass, the sum of all the particles, is simply m, and this distance is simply d, because we said the distance from the origin to this position is d squared. So this becomes d squared, and this is simply our ICM. This is simply our moment of inertia of the object if that object was rotating about the axis that goes through the center of mass. So we see that the moment of inertia of the object is equal to this formula, the sum of these two quantities. So that concludes the proof, and this proves that parallel axiom theorem is true.